Hello everyone, and welcome to Understanding Physics, in which I will try to guide you through understanding physics. So, today on General Physics 1, we want to talk about systems of particles, in which we will talk about the center of mass, and as well as the momentum, and we will later discuss what is the definition of collisions, as well as discussing something which we call as impulse. So, first we want to talk a little bit about the center of mass. So, what is the center of mass? The way that the way that I can describe the center of mass is that it is of the of the position. Well, basically it is the weighted average of the position. So let's just state if I have a very big object as well as a very small object, the the center of mass will be around here because on average the mass will be at around this position. So the way that you would write the center of mass is to be the sum of the position vectors multiplied that by the mass vectors divided by the mass of the objects over the total mass. And and so if you actually define this, so for the top one it is a discrete, but in here if we are talking about a continuous object, the way that you could write this down is something like this over big M. Let's just denote that to be the delta M there. And this will be the limit as delta M goes to 0. Delta Mi goes to 0. So yeah, the masses at each point will be different. So the delta Mi will go to 0. That means that the small masses will be very small. And therefore, you could write this down to be the integral of the r vector dm over the big mass. And this is for a continuous object. And so certain examples include if you have, for example, a triangular shape, you could do the integral as well as the masses. Let's just assume this to be a uniformly distributed mass. You could later do this integral, and later you would later figure out that the center of mass should be about 1/3 of its height. So you could do this for a practice problem for you to do. So some certain facts about about the center of mass could be taught if you actually remember Newton's third law as well as Newton's second law. So based on Newton's third law, we know that an object will exert the same forces on different objects with different directions. So for example, this is object 1, this is object 2, they will later repel each other. And so basically, this entire object have a have the total force to be 0, no matter what it is. But if you apply a force to the object, this will later result that the sum of this F would be the sum of the external forces. This is one fact that you need to remember. So basically the sum of the entire thing, no, sorry, the sum of the entire object will be only the sum of the force from the outside. While the forces from the inside, you don't need to know much about it. And so if you actually consider this, you could state this entire object to be a certain point. Let's just state that to be the center of mass. And then the center of mass will exhibit a Newton's second law motion, which is m times d squared over dt squared of the RCM will be the external force. So this is one of the properties that you could use to solve different kinds of systems. For example, if I have this triangle and I apply force, you could know where the center of mass is gonna move thanks to only knowing the forces from the outside. You don't need to know about its orientation as long as you know about its center of mass. And talking about orientation, it will later be discussed on the next chapter. So, we have discussed about this. So, if you want the proof of this to be true, you could just consider two different particles and finding its center of mass, and then if they exhibit a Newton's third law behavior, which is always, you would be able to determine that the center of mass wouldn't really change. So, that's about the center of mass. So we want to talk a little bit about momentum now. So, the way that we will talk about momentum is that we will actually define a object. The the total momentum will be the mass of the object, multiply that by the velocity of the center of mass. And so if you actually realize this much more further, you could figure out that the momentum of one single particle could be written as m times the v, the mass times the velocity, which we have already written in chapter 5 or chapter 4. And and this property here also also corresponds to the small scale version of the F equals to dp over dt. So in here, the external forces would be the dp dbp over dt. So there is a correlation between those two. So you would realize that if the external force is zero, the total momentum wouldn't change over time. And so this is one of the key things that you need to remember is that if there is no external force, no net external force, sorry, the conservation of linear momentum must be followed. Must be followed. So that is one of the important things for you to remember. So after we have talked a little bit about momentum of a system, we could start discussing about the kinetic energy of a system. So the way that we would actually try to figure this out is that we could just sum up each of the different velocities of the particle. And let's just give the reference point to be the center. So we would write this to be the sum of the half of the m of the half of the different masses, multiply that by the velocity of each different object, which could be written as the VCM as well as the V relative. And you would later square this. So, how would you actually... No, sorry, my bad. This will be the length squared. So if you actually try to open this cage up, you would later figure out that this is half mi vcm squared plus half mi with the v of the relative to the center squared plus half of, of the mi multiplied by 2, that's 1, and the v of the center of mass times the velocity in relative with the center of mass. And this part will later depend on your system. While you could actually figure out what's the velocity of the center of mass thanks to your knowledge of the movement of the center of mass. So you could write down that the total kinetic energy is the kinetic energy of the center of mass plus the kinetic energy from the object itself, which we call as the internal energy. And so this can be written as half of the big mass VCM squared. Because in the end, if you later sum up all the half mi VCM squared, all of the mi's will later be gathered up and become the big M, or the total mass of the object. So we have talked about the energy of the system, we have talked about momentum, we could start discussing about the collision. So a collision is basically a brief interaction between objects. So if you have a ball and also another ball, it will later have a certain amount of seconds in which these two are within contact with each other. And this could later result in a change in their velocities. So I want to discuss one of the useful things for you to know, which is something we call as impulse. So impulse is basically the change in momentum, which we could also denote as the j vector. And this is basically the integral of the f vector dt, or basically the force over the change of time. And so basically you could determine the change of momentum using impulse, which is the force times the change in time. So with this information, you could determine the interactions for a collision. So there are two collisions that I want to discuss. The first is a totally inelastic, while the other one is a elastic collision. So for a totally inelastic collision, this basically means that the object will stick together. Objects stick together. While in a elastic collision, the object doesn't lose kinetic energy. So that's basically the principle of a totally inelastic as well as a elastic collision. But there are also some other types of collisions which includes a partially inelastic collision. There could also be a explosion, which basically means that you add more kinetic energy to the system. Or if it is partially inelastic, partially elastic, it means that it is between the totally inelastic as well as the elastic collision. And so the way for you to solve to solve those problems is by using the conservation of momentum. So we will start by discussing the condition for a totally inelastic condition. So, for a totally inelastic condition, if you have two objects, let's say m1 with a certain velocity v1 and the second mass with the second velocity v2, these two must to equal to, well, the initial, this 2 must to equal to the m1 v final 1 plus the, okay, I2, plus the m2, the velocity of the final 2. So, in here, for a totally inelastic condition, we would see that the final velocities must equal with each other. Otherwise, the object won't really stick together. One of them will go piercing through, or maybe one of them is sliding off out of the entire object. So we must remember that the final velocities are the same. So you could later write this down to be m1 v I1 plus m2 v I2 must equal to the sum of the masses m1 plus m2 with a v final, with the velocity final. So that's for the totally inelastic condition. So this could work in almost any dimensions as long as you know what's the velocity, also the mass of both of the objects. So for a elastic collision, the way for you to solve this problem is not only by using the conservation of linear momentum, but you also need to consider the 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 conservation of energy. So, if you have these two objects colliding with each other, we want to make sure that the sum of the kinetic energy is constant, as well as the momentum is constant. So, if you actually first try to figure out the momentum of the first object, v1 plus m2 v2, this must equal to m1, well, these two are initials anyways, m1 v1 final vector plus m2 v2 final vector, the velocities. And so another thing that you need to consider is the kinetic energy. So half m1, the absolute value of v1 vector squared plus half m2 v2 initial vector squared is equal to half the mass 1 vector 1 final squared plus half m2 velocity vector of the second final velocity squared. So these are the two conditions you need to remember for a elastic collision. But not only that, if you're dealing with a one-dimensional case, which is the easiest one, you could write these down into two. m1 v1i plus m2 v2i is m1 v1f plus m2 v2f. And we could write the bottom one to be half vi1 squared plus half m2 vi v2i squared is m1 v1 final squared plus m2 v2 final squared. So half. So the thing that you could do to manipulate these results is that you could actually multiply the bottom side by 2, so you would later be able to obtain m1 v1I squared minus v1 final squared equals to m2 v2 final squared minus v1 v2 initial squared. So looking at this equation, oh sorry, uh, let's denote this to be the first equation. This is the second equation. This is from 2, and this one will be from 1. So we could also write the first equation into m1 v1I minus v1 final equals to m2 v2 final minus v2 initial. So you could write the top side. No, sorry. If you actually divide both sides, so these two divided and then these two divided, you would see that the m1s will later cancel each other out, and you would later obtain v1 v1 initial plus the v1 final is equal to the v2 initial plus the v2 final. So you could later figure out that this would mean that the v1 initial minus the v2 initial must equal to v2 final minus the v1 final. So this is one of the important things for you to remember, is that the total velocities must to be something like this. And so if you actually try to use a little bit of substitution, you you are able to solve for the final velocities for the first object as well as the second object just by substituting it towards the first equation or the second equation. So we will try to put it into the into this equation here. So we have the v1 final to be v2 final, subtract that by v1 initial minus v2 initial, and then we plug it in into the function 1, which is already transformed. It will be, oh sorry, my bad. We need to plug in the v2 final, sorry. So it's a plus sign. This would be 1, this would be 2. So if you plug in the v2 final, you would be able to obtain the m1 to be v1 initial minus v1 final, which is equal to the m2 of the v2, no, sorry, substituting it in, you would later obtain the v1 final plus v1 initial minus 2 v2 initial. So if you try to group them all together, you would be able to obtain the v1 final to be v1 final multiplied by m1 plus m2 is equal to m1 v1I, m1 v1 initial minus m2 v1 initial plus 2 m2 v2 initial. And so you would later obtain the v1 final to be uh, m1 minus m2 over m1 plus m2 v1 initial plus 2m2 over m1 plus m2 v2 initial. And you could do the same thing for the second uh, for for the second velocity. It will be 2m1 over m1 plus m2 v1 initial plus m2 minus m1 over m1 plus m2 v2 initial. So, and so this is the equation for you to use in a one-dimensional elastic collision. For a two-dimensional collision, the easiest thing for you to do is to actually to use components. And so you could later be able to compute the total momentum of each object just by summing up each of its momentums. So this is not written in the notes, but this is what I really want to encourage for you to know, which is to actually to write this down in matrix. So for a elastic collision, the way that you could actually write this down is that if you have the velocities, sorry, the final velocities, this would later equal to the multiplication of this matrix. m1 minus m2, no, sorry. You would just multiply everything by 1 over m1 plus m2. And the matrix is m1 minus m2, 2m2, 2m1, m2 minus m1. And so you could see that this is pretty symmetric. So, so that means that if you actually plug in the m1 first or the m2 first, it doesn't really matter. As long as you put it at the correct order, it is totally fine. So if you are able to use matrix multiplication, this is the best way for you to remember this formula. So we have discussed about collisions, momentums, as well as the center of mass. So in here, I have a simulation for you to actually to watch and to actually try to understand about the center of mass as well as momentum by 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 studying a nuclear reaction in which I will throw a proton, no, sorry, I will in which I will throw a deuterium, which is a element of hydrogen, with mass 2. And I will merge this with another one to form what we know as helium for 2. But technically this will later result in in the creation of a gamma ray, which I won't really discuss much since this will later be related to the propagation in the electromagnetic wave. So here is the simulation of a inelastic collision. So you could see here that I have a simulation of two different particles, the red particle as well as the blue particle. They are both colliding between each other, and then the X denotes the center of mass of the object. So, if you can see here, if you actually collide these two atoms together, it will later conserve its linear momentum, and it will later propagate in the direction of the total momentum. And so this checks out with the conservation of linear momentum. So that's all for today. I hope that that this lecture material will be beneficial for your studies. And if you want more of this, please consider subscribing, and it means a lot to me. So thank you very much, and I will see you on the next chapter. See ya.